Statistics are an incredibly important part of life. Yet most people, even in the sciences, don't take statistics courses. And often, when students are taking stats courses, they're steeped in mathematical formulas rather than the implications, use, and misuse of them. And yet, I'd agree with H.G. Wells and only update it to say that it really is necessary now for efficient citizenship. We just haven't fully updated our education system to include this. The easiest to understand explanation of p-hacking that I have ever seen is this XKCD comic. Remember from our readings that p less than 0.05 means that we reject the null hypothesis, effectively claiming a likely link between two things. So here we have scientists investigating the link between jelly beans and acne. They originally don't find the link, but then a kind passerby claims that it's only certain colors, and so they go on to investigate all the jelly bean colors, or in this case 20. Yet, if our p is 0.05, that means that if we test 20 different items, we actually would expect that one would be significant by chance alone. Or, if you prefer, for easier math, if we test 100 relationships, we would expect 5 to be due to chance alone. Given that it's pretty unlikely that green jelly beans will actually cause acne, but rather that the limitations of our test threw up that one by coincidence. If you wanted to then go on and test this and check it, you would need to go and run an entirely new experiment, one that did not include any of the data or participants from this experiment, and test it again. If again, everyone except the green turns up null and the green shows a relationship, you might be able to say, okay, there's a likely correlation here. Of course, we'd still need to account for all the issues we talked about in our correlation versus causation lecture, but as this comic stands here, you really can't even say that there's a likely correlation. In literature, this occurs when they're testing lots and lots of variables. Sometimes this can come up because of testing large numbers of unrelated subgroups. For instance, if you're testing age ranges and you test 100 different groups of age ranges with p less than 0.05, then 5 would be expected by chance. And it'd be a bit odd. Now, that doesn't mean that large numbers of subgroups are necessarily a problem. When we are specifically looking for the effect of demographic variables on things, we often need to test a lot of subgroups. However, you need to account for what may or may not happen by chance at that point. So for instance, if you test 100 different subgroups and you get 5 that show a p less than 0.05, you don't report those as likely correlations. You may say something like, which is no more than is expected by chance, so while further investigation is warranted, the reader should be careful in their consideration of these values. So that you're clearly stating that these are most likely due to chance while still reporting your data out to the public. I know that this tool that I'm going to have you do is not scientific literacy exactly, but it does a great job of showing how with enough data and enough variables, you can basically say whatever you want. It lets you p-hack in real time with real data, and it's really kind of cool. So on your own, fiddle with the settings until you get p less than 0.05 for 2 settings that would make it appear that Democrats are good for the economy, and 2 settings that would make it appear that Republicans are good for the economy. You can either go ahead and turn this in on your own, or when you get into your group, you can combine them all into one document as well, if you all want to have matching documents, whatever is easiest for you. But I'd play with it a bit on your own before getting into groups, since this really isn't a great online group activity, but I do want you to talk about it in your groups. Another issue that comes up is actually another fallacy. This is called the Texas Sharpshooter fallacy, which comes from the analogy used to explain it. The idea is that if you shoot at a barn completely randomly, the bullets will clump together. You could then go and draw bullseye around the clumps of bullets, making you seem like an amazing shot. This idea goes hand in hand with p-hacking. If you put enough variables into a calculation, you will get some statistically significant results purely by chance. And then you can go in and explain why those things cause whatever it is that you're studying. Now, this leads into post hoc storytelling because you're then, after the fact, explaining why this result is significant. Now, there is a fine line between explaining a viewed relationship versus telling a story to explain something that you weren't expecting or don't understand. Whenever possible, an explanation should have some proof of plausibility, but plausibility is never enough. Other literature that supports it should be present and should not be too far removed. That being said, all of that is really difficult to judge if you aren't an expert. It's usually easier to spot the p-hacking than to spot the post hoc storytelling. So what should we be watching for? If there are lots of variables that aren't needed or don't have any real plausibility or rearrangements of the options that there are. So for a not particularly random example, if you are testing If you are not just testing ibuprofen usage and acetaminophen usage, but relationships to vaccines, but are also testing whether they're taken before or taken after, even though the plausibility of why that would matter is basically non-existent. Or testing very small age groups without a specific reason. The second one is harder, because actual explanations describing a phenomena and post hoc storytelling is very, very similar in some cases. This is one of the reasons scientists are supposed to do hypothesis testing, as it helps to minimize post hoc storytelling if you give your explanations in the beginning. However, lots of discoveries do happen on accident, so we don't want to write off any result that didn't come directly from the hypothesis. Usually to catch this, it either needs to be pretty outlandish, like the example of your reading today, or more often it seems like the story is always changing. For example, in one study by the group, a certain combination of medicines affect one age group, but then in the nearly identical study done, suddenly it affects another age group, things of that sort. And one of the biggest red flags is that an experiment is stopped prematurely for anything other than safety issues. Medical trials go so far as to make you state what numbers you need to have your statistical power before you start the experiment. In order to end it early or go longer, you must get approval from the FDA or another agency. But non-medical trials don't have that safeguard. Researchers can choose to end their data collection at any time. This one is generally a bit more nefarious, as it's a known way of messing up your own data, and so it's pretty easy to avoid. But if motivated cognition is strong enough, it doesn't have to be nefarious. My personal belief is that no study should ever be ended early without a full explanation in the journal article about why it was, and what this means for the results. However, you'll absolutely see people do it with no explanation other than, and we got approval from the FDA. It's hard to be able to judge for yourself in that case if the ending of the trial was something to put into possibly sketchy column, or if you want to put your full trust in the governing committees. They're just humans with their own biases, so personally I would like to read for myself why it was ended early. The next statistical issue we will discuss is sample size. If we're talking about a medical trial, this is generally the number of patients. In other fields, it's usually something similar. In medical studies, generally this is chosen in order to have sufficient statistical power to meet a specified endpoint. This, of course, can be really tricky to figure out. Ideally, you need to know the things listed here in order to calculate it, but there are methods to do this that we aren't necessarily going to get into here, other than to state that you should do them if you are going to do these experiments. As a general rule, larger sample sizes are best. The easier the data is to collect, the larger you expect it to generally be, as there isn't any particular savings to not doing so. Something that often comes up is people being concerned about differences in sample sizes. This isn't really an issue so long as both samples being compared are large enough. So, for instance, if you are comparing some health impact on different genders, and you have 10,000 males identifying, 100,000 females identifying, and 10 identifying as non-binary, you can certainly make conclusions when comparing males to females. Even though they are different, 10,000 is a really good sample size, even if it is a whole lot less than 100,000. However, 10 by basically any standard is going to be too small of a sample size to tell you much, and likely won't be able to accurately use most statistical methods on that sample. Now, having a low sample size doesn't always mean you should completely distrust the paper. There are a lot of reasons that a sample might be small. Usually, legit reasons for small sample sizes involve cost, time, difficulty in recruiting, rarity, or safety. But even if this low sample size is for a good reason, it does mean that we have to take that data with a grain of salt. Often these will be trials to test and see if future trials can be done. For instance, phase 1 trials in drugs are normally quite small, as they are the first to test safety in a human population. But this can give us enough information to decide if it's worth moving on to phase 2, though not enough to decide if the drug actually works. The other time that small sample sizes aren't a significant problem, and what this meme here is getting at, is if the effect size is so big that it shows through even in a small sample size. For most medical studies, an n equals 20 would be considered quite small. But if those were terminal cancer patients and suddenly the drug cured 15 of them, that would indicate something really important and special happened and should be paid attention to, even with a small sample size. We're probably going to want a larger sample size before we make any sweeping recommendations about it, but it is a meaningful result. Now, take a moment and read through the following excerpt and discuss the questions with your group. If you have enough time, I'd recommend going to the second link and reading through the entire article. However, for brevity, I've condensed it quite a bit for your Google Doc. Regardless of if you go to the actual article or not, perhaps mentally bookmark Science-Based Medicine as one of those really trustworthy sites to go and learn about things. This is a place that, if you want to be able to blindly trust experts, is generally quite safe. If you come across a medical topic in the news that is at all controversial, you can go there and get a pretty good rundown of what is happening, what the controversy is, and if the controversy has any legitimacy at all, and why or why not. I do have one important note on question 6. This will ask you for topics that you are unpersuadable on. Try to avoid topics where it's just the preponderance of evidence is so high that it'd be next to impossible to convince you. For instance, the Earth is not flat. Aim for topics where there is some wiggle room. To give 2 examples from us to help you with this, and also to help you not feel too silly if you want to suggest something that goes against the scientific mainstream, I think that I'm nearly completely unpersuadable in the fact that chiropractic works. As a child who had debilitating headaches that chiropractic fixed, and I have significant back and rib issues that require constant adjusting, I'd probably be on narcotics if it wasn't for the pain relief it provides. And this absolutely goes against the weight of the evidence that can't seem to find effects beyond that of a simple massage. I actually find it incredibly difficult to think of any possible study that could be done that would stop me from utilizing it. I do have one important note on question 6. This will ask you for topics that you are unpersuadable on. Try to avoid topics where it's just that the preponderance of evidence is so high that it'd be next to impossible to convince you. For instance, the Earth is not flat. Aim for topics where there is some wiggle room. To give you an example from me to help you with this, and also to help you not feel too silly if you want to suggest something that goes against scientific mainstream, I think that I'm nearly completely unpersuadable on the fact that chiropractic does work. As a child who had debilitating headaches that it fixed, and had significant back and rib issues that require constant adjusting, I'd probably be on narcotics if it wasn't for the pain relief it provides. And this absolutely goes against the weight of the evidence that can't seem to find any effects beyond that of simple massage. I actually find it incredibly difficult to think of any possible study that could be done that would stop me from utilizing it. It's also best if you can think of things that actually affect your life and decision making. For simplicity, I'm going to go ahead and just put my discussion on the questions on your sheet in this same video. So pause here and come back after you are done talking about it with your groups. Same idea as before, of course you could go on, but hearing the instructor's answers is totally going to hamper your discussion and thoughts on it. There aren't really right or wrong answers to these, so it's better if you think on it before hearing my thoughts. So pause now and come back when you're ready. Often, for number 1, people will talk about auditory or visual hallucinations. Nothing crazy, just simple things like thinking you heard your phone buzz or heard your cat make a noise. My favorite version of this is actually a tactile hallucination. If someone even mentions someone having head lice, your scalp will begin to crawl, sometimes for hours after the person mentioned it. You're welcome for that one. For number 2, one of the simplest examples of this is testing of different races. We know, for instance, that test scores, whether it be IQ or others, of African American and whites have significant gaps. A researcher who subconsciously believes that African Americans are less intelligent is likely to control for and measure subtly different things than someone who believes testing cannot ever measure IQ. And different yet from a person who believes systemic racism is the cause. And even though all researchers believe that they are completely unbiased and have the absolute best of intentions, the subtle experimental design aspects that they miss are going to differ and can lead to completely different conclusions about the reasons and what we should do about it. So for number 3 and 4, generally the easiest place to find this is to think of a time that you got in a fight about something that seemed non-personal. That afterwards you regretted what you said or realized you were really wrong about something that normally you wouldn't have been wrong about. It's usually easier to spot in others than yourself. Facebook and Twitter are great resources for finding these. Number 5. This is basically just me asking you to talk about what we talked about in the motivated cognition class. If you had trouble, review the concepts there, or bring your example to class and we can talk about it there. Number 6. I talked about this one before, but hopefully you thought of some. These make great discussion points and would be a lot of fun to chat about in class if you'd like to share them there. But the main idea is that when you are unpersuadable about something, you are going to need to pay attention to your thought processes and your biases on any articles that come out on it more carefully. So the more you're aware of what you're unpersuadable on, the more you're going to be able to decide when to have those discussions, if to have those discussions, and how to take in the scientific literature on that. Number 7. This is pretty similar to the previous questions in many ways. It pervades the way we do science, the way we read science, the way we collect science. It is confirmation bias, motivated cognition, and a random assortment of all the other biases we talked about depending on the person or topic. This discussion is really not a detailed report on these questions, as they really are discussions more than lecture questions. So please stop by class and talk about any issues you had with or aren't clear on it. We can talk about your individual thoughts and examples as well.